Section 10. The main topic of Section 10, what takes up the largest fraction of it, is about standing waves. But before we get to that, there's another thing that I've thrown in here. I had said earlier, somewhere in Section 9, I think, that the loudness of a wave corresponds to its amplitude. Well, that's one way of doing it, but it's not the way people usually look at it. What's typically done is to describe the loudness of a wave in terms of how much energy it carries, rather than the distance that the molecules get shook back and forth. The one thing is related to the other, obviously. Waves with, well, maybe I shouldn't say it's obvious, but waves with larger amplitudes have, they carry more energy. If you think about water waves, if you picture yourself sitting on the end of a dock, and there's some cute little water waves going by with an amplitude of 5 or 6 inches, well, that's kind of fun to dabble your toes in sometimes, I guess. On the other hand, if the waves have an amplitude of something like 10 or 15 feet, you really don't want to be sitting on the end of that dock, because among other things, the dock is going to get smashed into a pile of toothpicks. So the higher the larger the amplitude, the more energy that the waves carry. You don't need to get into it in this much detail, but it turns out to be that the intensity is proportional to the square of the amplitude, if I remember right.
Lucia Sprague and Marilyn Krupa, please come to Mr. Rapone's office.
Well, that's been immortalized in the recording, I guess.
Morning.
Oh, good morning.
I understand you fixed that.
Yeah, I'm going to pause this for a second.
That's good.
Okay, the intensity of the wave is defined as the power per unit area, where power, that's something that first got introduced in Physics 121, actually. Like it says underneath here, power is the rate that energy is being carried, the energy per unit time. A joule per second is a watt. And intensity is described is measured in watts per square meter. So instead of how much the air molecules move back and forth, you could talk about how many watts per square meter the wave carries. Actually, with light waves, that is sometimes done. Not usually with sound waves, though. The problem with measuring in watts per square meter is just that there is such a range. From the faintest sound you can just barely hear to the loudest sound that you can stand without wanting to put your hands over your ears, you're talking about roughly a factor of 1 trillion. The threshold of hearing is around 10 to the minus 12 watts per square meter. And the threshold of pain, of course, these are figures that vary some between individuals, but the threshold of pain is somewhere around 1 watt per square meter. So rather than have numbers where you're always counting a whole lot of zeros, what's more convenient is a scale based on the logarithm of the intensity rather than the intensity itself. But that's further down the page. I'm getting a little ahead of myself, I guess. Before we get to that, the way that loudness drops off with, well, not just loudness, this could be the intensity of light. It behaves the same, any kind of a wave that's spreading out in 3 dimensions drops off as the inverse square of the distance. And actually not even waves. We've seen Coulomb's law, the strength of an electric field drops off as 1 over r squared. The strength of a gravitational field drops off as 1 over r squared. The reason is, if you've got a source of pretty much anything. Oh, that's aimed much too low. I mean, it could be some sort of a lawn sprinkler throwing water in all directions, as long as it's throwing it uniformly in all directions. As whatever the stuff is that's being sprayed out in all directions. At a distance of R1, it passes through a sphere whose surface area is, well, just a sort of a footnote here. The surface area of a sphere. Surface area of a sphere is 4 pi r squared. So if you want to know how many watts per square meter of light, or if you want to know how many drops per square meter from being sprayed from a lawn sprinkler.
Marilyn and Lucy, could you come back for a second?
At a distance of 1 meter, that would be spread over 4 pi square meters. As the drops of water or the sound energy or anything else travels further outward, as they pass through this imaginary surface, well, with twice the radius, you're going to have 4 times as much surface area for it to be spread over. And at 3 times the radius, you'd have 9 times as much surface area for whatever it is, in this case, the energy of a wave to be spread over. So that's the reason you can read a newspaper if you're sitting right under a street light, but if you go half a mile down the road, you can't, unless there's another street light. It's because the farther away you are, the more area, the more spread out the wave's energy becomes. You have less per unit area, which makes light dimmer and sound fainter and so on. So anyhow, the intensity of anything that's spreading out evenly in 3 dimensions, such as the brightness of light, the loudness of sound, it drops off as the inverse square of the distance, like in the second little box here. So now we have an example for you to work on. Basically, it just gives you some numbers to stick into that inverse square law. And I'll hit pause to let people work on that. Section 10, number 1. So from the box just above the question, intensity at point number 1 over intensity at point number 2 equals the radius out to point number 2 squared over the radius out to point number 1 squared. And as I seem to end up saying just about every
And the
day,
modified gold team, please report to the cafeteria to meet with Mr. Ferris. It's important. The modified gold team to the cafeteria.
he's using that PA system more today than usually in a whole week put together.
I wish they would shut it off.
I suppose we could like cut the wires or something, but anyway, as I seem to say with great frequency, you can put the numbers in first and then do the algebra. You can do the algebra first and then put in the numbers. I quite often do the algebra first because once in a while something cancels out and makes it simpler, but it doesn't really matter. whether the numbers have been put in or not, you're going to multiply both sides by R1 squared in order to solve it for R2 squared. And then finally, take the square root of both sides. Fill in the numbers. Point number 1 is 10 meters away from the source. Now, one mistake that comes up sometimes is people just simply switch the numbers. As with most kinds of problems, it's not a bad idea when you get to the answer to look at it and ask yourself if it makes sense. If you're if the light is going to get brighter, that should mean you're getting closer to the lamp. And if the answer says you're getting farther away, that probably means you switched a couple of numbers somewhere and you want to go back and look for it. So the 10 meters should correspond to the number on top, R1, I1. When you're 10 meters away, the intensity is 1,000. So because it's an inverse square law, changing the intensity by a factor of 2 doesn't mean the distance changes by a factor of 2. It means the distance changes by a factor of the square root of 2. Okay. I'll pick it up again over here. So, as I started to say a couple minutes ago, so that you're not dealing with such a wide range of numbers, it's convenient to use a scale based on
Any remaining student seventh and eighth graders that are in the building, please report to Mrs. Babcock's room.
Believe it or not, sometimes they go this whole half hour without ever saying anything on that PA system at all. Not only does using a logarithmic scale compress the numbers down into a more manageable range, but it's not a perfect match, but it comes closer to your perceived sense of loudness also. As we'll see as we go further down the page here, if you compare 60 decibels to 80 decibels, 80 decibels is 100 times as intense, meaning that 100 times as much energy gets absorbed by your ear every second. But it doesn't sound 100 times as loud. Okay, so a logarithmic scale sort of comes closer to your perceived loudness also. So for several reasons, the sound level in decibels is defined according to this formula here. And underneath, I put a quick little summary of what a logarithm is. For most purposes, you can just think of it as a button you push on your calculator. But the underlying idea is that a logarithm is the inverse function to an exponential function, okay? If x is equal b to the y, b is a number called the base of the logarithm. For example, b might be equal to 10. So y, for example, might be 3. So 10 to the third power equals 1,000. That makes 3 the logarithm of 1,000, log to the base 10. Anyhow, you can have logs to all sorts of different numbers. The two most common versions well, one is actually called a common log, which is a log to the base 10, like I was just talking about. The other is a natural log, log to the base E, where E is a transcendental number like pi that just goes on and on without ever repeating or terminating. So anyhow, the way it works, I guess I'm more interested that you understand how it works than you know, the being able to recite the definition or something like that. The way it works is that every time you multiply the intensity by 10, you add 10 to the number of decibels. So, for example, well, I mentioned a minute ago that 80 decibels is 100 times as intense as 60 decibels. Here it says 80 decibels is 1,000 times as intense as 50, because 50 to 60, 60 to 70, 70 to 80, that's 3 factors of 10 that you multiply together. 10 times 10 times 10 is 1,000. So, you know, if you wanted to compare 90 decibels to 50, that would be 10,000 times as intense. Every time you multiply the intensity by 10, you add 10 to the number of decibels. Just a few examples. Yeah, like a fairly quiet library might be, I don't know, I don't have this written down in front of me, but I want to say that would be around 50 or 60 decibels or something, maybe even a little lower, depending on how the people in the library are behaving. The legal limit for continuous occupational exposure is, oh, I think there's 2 different government agencies with slightly different standards. I think one of them uses 85 decibels and one of them uses 90. But the idea is, if it's your job to sit next to a machine that gives off 90 decibels, and you have to sit there next to that 8 hours a day, 5 days a week, all year long, you're supposed to be using earplugs or headphones or some kind of hearing protector. It's required by law that your employer not expose you to louder levels than that without protection. I believe it's 115 decibels, which is the legal limit for any exposure. Like if you're just going to be exposed to it for 1 second, at 115 decibels, you're supposed to have some sort of hearing protectors. 115 decibels is also not unheard of at a concert. It's not a workplace. OSHA regulations don't apply. And certainly these people, you hear them coming down the street from about a mile away, you know, and it's mostly the bass that manages to get through. You know, boom, 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 boom. Yeah, those guys aren't going to be able to hear it by the time they're 30 or 35. Because what you see, the insidious thing about sound is that it starts to hurt you before it hurts. Okay. Yeah, really loud sounds become painful, but at somewhat lower levels, what it does is it just gradually wears out your ears. Okay, the inner ear just gets desensitized, kind of worn out, and your hearing sensitivity gradually erodes, and once you lose it, you're not going to get it back. So that's why when the muffler rusts off the lawnmower, you should probably replace it. Like my father didn't when I was a kid. I'd get off that lawnmower and my ears would be ringing. Anyway. Example. Actually, there's 2 examples. So maybe I'll boost it up a little bit in case somebody's trying to follow this without a printed copy of it next to them. And we're going to pause it there. Number 2 asks you to find the intensity in watts per square meter from the sound level in decibels. Well, if all you had was this equation on the left, what you would have to do to solve, because it's asking for I, to solve that for I, you'd have to first divide by 10, and then you'd have to take the exponential function of both sides, 10 to the x of both sides, to get the log off of there. And then finally multiply both sides by 10 to the negative 12. And well, I thought I'd save you a little trouble. I did all of that. And the end result that you get is the version that's over here on the right. So the box on the right is really the same equation as the box that's on the left. It's just been algebraically rearranged to set it up for a question that asks you how many watts per square meter. That's what's on the end here, W over M squared. Those are units, not something that you're supposed to stick numbers into. So what number 2 is asking you to do is just take the 74 decibels, stick it into this formula for beta, and then the rest is just calculation, which would look like this. Formula once again was that intensity is 10 to the beta over 10 minus 12. It's kind of a big cluttered up exponent. We're going to stick in 74 for the number of decibels. So that's 10 to the 7.4 minus 12. In other words, 10 to the negative 4.6 power. So there's probably a 10 to the X button on your calculator. You would just put in negative 4.6 and then push that button. Or if not, you know, the way it is on a lot of calculators, you put in 10 and then there's the caret, and then you'd put the negative 4.6. Or if you have any trouble figuring out how to work your calculator, ask me about it sometime. It should come out 2.51 times 10 to the negative 5th, and that's measured in watts per square meter. And then we have number 3. So part A of number 3 is going to just be a repeat of what I just did. But then part B, once you have the intensity, you stick it into the inverse square law. See, the usual mistake when there's a problem kind of like this one, where it says, here's the decibel level here, what's the decibel level over there? People stick the number of decibels into the inverse square law, and the number of decibels does not obey the inverse square law. It's the intensity that goes as the inverse square of the distance. So you have to find watts per square meter from the decibels, put the watts per square meter in the inverse square law, and then finally find the number of decibels that corresponds to that. And in this question, that's been broken down into steps for you, but that might not always be the case. So to begin with, part A, same thing I just did, but with different numbers. 10 to the 80 over 10 minus 12. The intensity 25 meters from the machine is 10 to the negative fourth watts per square meter, 1 times 10 to the negative 4. So then to get the intensity 40 meters from the machine, gotta relocate the camera. Out there. Well, on the formula sheet and in the notes, it calls the intensities I1 and I2. But maybe to make it a little harder to mix things up, why don't I call them I40, as in the intensity 40 meters away, and I25, the intensity 25 meters away. And the reason that it's an inverse square law is that if 25 is on the bottom here, 25 is on the top there. And if 40 is on the top here, it's on the bottom there. So the intensity at 40 is what we're looking for. So multiply both sides by intensity at 25, drop in the numbers. We know the intensity to put here, it's the answer to part A. Don't forget to square. As far as the units, meters here cancels with meters there, leaving you with something dimensionless. Whatever unit you've got on I-25 will be the unit that's on I-40. And then finally, what's the sound intensity? Well, then you take this number and stick it back in the formula for the number of decibels. .9, just like it says underneath the question. Okay, so that's the thing about loudness in the decibel scale. And then we move on to the superposition principle. Gotta put another couple books under there. When waves collide with each other, it is, in a sense, the opposite of how particles behave. If you have two balls run into each other on a pool table, they bounce off. If you have two waves run into each other in a bathtub full of water, they just pass right through each other as if the other one wasn't even there, and they keep on going. The superposition principle describes what happens while you have both waves in the same place at the same time. And basically what it says to do is you just add them together. Okay, in a three-dimensional situation, then you'd have to get into a full-blown vector treatment with components and all of that sort of thing. But if you're just talking about waves on the surface of some water where there's only two possible directions, the water can either be pulled up or pulled down. You just call up positive and down negative. And what the superposition principle says to do is you just add them together. At that moment when both waves are in the same place at the same time, what does it do to the water level? Well, for example, if one wave wants to pull the water level up by 2 millimeters, that's what would happen if that one was the only wave present. And at the same point, if the other wave was the only one present, it would pull the water down by 3 millimeters. Then if you have both present at the same time, what happens to the water level? +2 added to -3 gives you -1. The water level would be 1 millimeter below its equilibrium position. That's the superposition principle, which is kind of what you build on, not only to talk about standing waves, which is what we'll get to when we turn the page here, but any other kind of interference of waves, which we'll also look at a little later in the course. I don't know if that's next week or the week after that, but sometime soon. So, standing waves. Yeah, one more. There we go. So let's say I was standing at one end of a long clothesline. And well, it doesn't have to be that long, I suppose, but I grab one end of it and I start shaking it. Okay. This is pretty much what you're going to do when we get to the lab for this part, except, I just put that away the other day because another class did it. I should have just left it out a little longer. But you're going to have a long spring. It's nice and heavy, which makes the waves travel slowly, which is helpful. But anyhow, whether it's a clothesline or the spring in lab number 10, you grab one end of it and you start shaking it with your hand. And waves travel along the cord from your hand. Well, they get to the other end before very long. Waves can't just disappear, they carry energy. And if it runs out of clothesline, there's no place for it to go except turn around and go back the way it came. So the wave reflects off of the end. And so now it's traveling back toward your hand. Well, in the meantime, you haven't quit shaking your hand. So you've got the newer part of the wave headed away from your hand. And then the older part of the wave that's already bounced off the other end, it's coming back toward your hand. And the way these two waves superpose with each other, the way they interfere with each other, if you want to use that word instead, creates this pattern called a standing wave. And I kind of made a little illustration here. The idea is the solid line is as the rope or whatever it is vibrates back and forth. The solid line is the farthest it ever goes in the one direction, and the dashed line is the farthest it ever goes in the other direction. So any given point along the rope vibrates back and forth within this envelope that I've sketched here. Notice that every so often there are points that don't move. As the waves pass through each other, they always cancel. Well, if both waves have the same amplitude, they both cancel exactly at those points. if one wave has a little bigger amplitude than the other, then there'd be a little bit of vibration there, but the node would at least be a minimum point of vibration. So anyhow, the points that don't move are called the nodes of the pattern. The maximum points of maximum vibration in between are called antinodes. And you'll get a good look at this sort of thing for yourself when you do the lab. Most of the not all, certainly not all, but most of the applications for this sort of thing are on musical instruments. That's what we'll talk about the most anyhow. When you set up vibrations on a guitar string or a piano string or something like that, you're creating standing waves on there. But there's also other applications like even in architecture. If you build a skyscraper and then an earthquake starts shaking that skyscraper around, it will create, I should probably make a couple of diagrams. I used to have a vehicle where the radio antenna would get standing waves on it sometimes if you're driving the right speed, and it seemed to help if it was raining. But there was the fender there, and you'd see the antenna kind of vibrating back and forth like that. You have to have a node at a fixed end because, you know, the antenna is attached to an immovable object there that forces it to have no vibration. It forces in, you know, a node is a point of no vibration, and a free end has an antinode. This actually is vibrating at the second resonant frequency. The fundamental mode of vibration would be if it just went back and forth like this. Well, it's kind of cute when it's on your radio antenna and you're watching it through the windshield. On the other hand, if this is a skyscraper and you're on like the 75th floor, it's not as much fun. And if you're designing this sort of thing, because you know, without any precautions, this could shake a building apart. And actually, that's something that's fairly famous among physics type circles. The Tacoma Narrows Bridge in the state of Washington, this was not a small bridge. This was a big suspension bridge. And shortly after it opened, the wind came up one day and it was just like a bow going across a violin string. And it set up standing waves on the bridge, which shook it apart and made it collapse. Fortunately, it didn't collapse immediately, and so there wasn't anybody on it. I think maybe a dog got killed or something like that. But anyhow, not all of the applications of this sort of thing are in musical instruments, but a lot of them are. So anyhow, you create these standing wave patterns from having identical waves pass through each other in opposite directions. The simplest case would be just one wave going in each direction like I was talking about, but you know, on something like a guitar string, actually a wave will go back and forth hundreds of times before it finally dies out because of friction. A more complicated version of the same story. Well, this is significant. I might have even put it on the formula sheet for you. I don't remember. I'd have to look. I probably should have if I didn't, but notice that, maybe I should use this pointed over here again. So the solid line is the farthest it ever goes to the one side. The dashed line is the farthest it ever goes to the other side. And pattern might continue on beyond here, but, well, this is what I'm interested in. You've got a node there, you've got a node there. Notice that the nodes are only half a wavelength apart. This is a common source of error. People use the node to node distance for the wavelength, or the antinode to antinode distance for the wavelength. But if you were to come up with a camera and take a photograph so that you froze an instant in time, what you'd see on that photograph, if you took it at the right moment, would be this solid black line here. Or if you took the photograph half a period later, then what you'd see on the photograph would be the dashed line. Well, notice that from here to here is only the top half of the wave, okay? One complete wave is from there to there, the peak and the trough. So node to node is only half a wavelength, like it says there. Wavelength is 2 times the distance from node to node. I guess it's time for another book. Likewise, antinode to antinode is half a wavelength. Node to antinode would be a quarter of a wave. And that will be sort of an important thing to keep in mind when we get to the next example. But before we get to the next example, some more background information. The word resonance is when well, first of all, resonance is something that occurs in any system where you have driven oscillations as opposed to free oscillations. Simple example would be a kid on a swing at a playground, which is basically a pendulum, okay? You just, you've got like a little 3-year-old kid. You just pull it back, let it go. If you just stand there with your arms crossed watching, that's what I mean by a free oscillation. It just goes back and forth. If you're pushing every so often on the swing, that's a driven oscillation. You are providing a periodic driving force. So just instinctively, because doing it any other way would be kind of stupid, you make the frequency of your driving force equal to the natural frequency that the swing freely vibrates with. If the swing goes back and forth once every 2 seconds, you push on it once every 2 seconds, but you don't have to. Those are 2 distinct things. The swing's period and the period that you push with. And if you pushed with almost any randomly chosen number for how often you push it, the swing is just going to kind of quiver around. Like if the period is once every 2 seconds, but you push on it once every 2.1 seconds, well then, the swing comes over and you push on it just as it turns around, okay, and it comes over, and then it's 1/10 of a second into the next cycle before you push on it the next time, and it goes over and it comes back, and then it's 2/10 of a cycle, 2/10 of a second into the next cycle, and then the next time you push it, it's 3/10 of a second in, and before very long, the swing is coming back towards you when you push on it. And aside from any issues of making the kid mad and getting broken fingers, another problem with this is that if you're pushing on it in the wrong direction, you're taking energy out of the pendulum instead of energy adding to it. So for almost any randomly chosen frequency that you push with, the swing is just going to quiver around a little bit. But if you make the frequency of your driving force equal the natural frequency of the swing, then you're always pushing in the right direction. And on every stroke, the amount of energy in the swing gets a little more added to it. And before very long, you build up a large amplitude. That's resonance, okay? If you drive the thing at its resonant frequency, you get a large response. If you try to drive it at some other frequency, you do not. So this is something that's found in several types of, different, really anything where you've got driven oscillations. Back in unit 8, actually, you already saw, those of you who are in there, already saw resonance in an electrical circuit. But today we're talking about the resonance of standing waves. So there are certain special frequencies where you can shake a clothesline, for example, where it will vibrate with a large amplitude. If you shake it with any other randomly chosen frequency, it's just going to quiver around a little bit. Okay, so that's what resonance means. When a driving force creates a large amplitude vibration due to driving a system at its resonant frequency. Da, 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 da. Always pushing in the direction it's already going. So what are the resonant frequencies of a clothesline or a guitar string, or, they're all basically the same thing. Well, those are determined by the conditions that must be met. The technical term here is boundary conditions. The boundaries in this case meaning the ends of the string. And I already mentioned, actually, that if you're talking about some sort of a vibrating cord, which might be a poor choice of words if you're talking about an antenna or a skyscraper or something, but some sort of, transverse waves on some sort of a line of some kind, you have to have a node at a fixed end, because if you prevent it from moving, a node is a point that doesn't move. And you also have to have an antinode at a free end, at least if it's a completely flexible line. You do. Antenna wouldn't be quite that flexible, but similar story. If you're talking about musical instruments, you've always got a fixed end, okay? If you've got a guitar string with a free end, you stop playing until you put a new string on the guitar. So while it comes up in some other situations that you might have a free end, if you're talking about guitars and pianos and violins and things like that, all you have to worry about is what happens at a fixed end. And at a fixed end, the string has to have a node. Since the nodes are half a wavelength apart, the length of the string has to be a whole number of half wavelengths. In other words, if from there to there is the length of your clothesline or guitar string, it could vibrate with this pattern, back and forth between those extremes. That has a node at each end, as is required. Or, I'm going to do that a little too long. Well, like that maybe. It could go back and forth between these extremes. Once again, you have the nodes that are required at the ends and another one in the middle. Or, let's see, about there and there maybe. could go back and forth between those extremes. A note is required at each end, and we'll throw a couple others in between, and so on and so on. Here, the length, maybe L for length. Here, the length of the string is half a wavelength. Here, the length of the string is 1 wavelength. Here, the length of the string is 1.5 wavelengths. The next one would be where it's 2 wavelengths, and then 2.5. And so, because of this condition that must be met at the ends, the length, there's only certain wavelengths that can exist on this string. The ones that meet the condition I just mentioned, half a wavelength, 1 wavelength, so on. Because there are only certain wavelengths possible, the string can only vibrate with the frequencies corresponding to those wavelengths. And those would be the resonant frequencies of that string. Okay. So where are we in the script here? String must have a node where it has a fixed end. I think I said that pretty thoroughly. The string must hold a whole number of half wavelengths. The special frequencies obeying that condition are the resonant frequencies. I don't know why I couldn't have written out the word frequency. Wouldn't have taken that much longer, but it is what it is. So, based on those ideas, I want you to calculate the first 3 resonant frequencies of this clothesline that question number 4 talks about. Basically, what you need to do, just to give you some hints before I turn you loose on it, is the lowest frequency would correspond to the longest possible wavelength. That would be when the string vibrates with this pattern. Now, the question tells us, where are we here? We're on the next page. Question tells us that L is 3 meters. So when it vibrates in this pattern, 3 meters is equal to half a wavelength. Once you know the wavelength, you can calculate the frequency, F equals V over lambda, because the question tells you the wave speed. Next lowest frequency would correspond to the next longest wavelength. That's when it vibrates in this pattern, where the length of the string would equal the wavelength. And then the third one would correspond to this pattern, where the length of the string equals 1.5 wavelengths. In each case, then you calculate the frequency from the wavelength, and that's how you do it. Now, what I think I'll do is, instead of going over this now, we're just about out of time. I'll go over it at the beginning of the next class. So till then.